Hi, this is a video for AP Chemistry. We are going to be discussing valence shell electron pair repulsion model and molecular structures. So valence shell electron pair repulsion is when the electrons that are in bonds or lone pair electrons are going to repel one another and try to arrange themselves far apart as possible so that they can minimize repulsion. The geometry of the molecules really then depends on how many electron domains there are, which that includes the bonds and the lone pair electrons. If you do have a bond, a single bond counts as one domain, but so does a double and a triple. Lone pair electrons tend to require more space, and they will kind of compress the angles of the bonding electrons, bonding pairs. And this diagram is here to kind of explain. So if you have an element X and an element H, the pink is representing the electrons in the bond between them. And you can see that maybe X has a higher electronegativity, but overall the electrons are between the two atoms because they're mutually attracted to both of the nuclei. Whereas over here, the pink is the electron again. If there isn't another atom over here on the right, kind of attracting the electrons away, then they're going to arrange themselves as close as possible to the positive nucleus. And because of that, they do push on any other bonded electrons. So we are going to switch to a note packet right now. So if you don't already have this, you'll want to grab it and print it out or pick it up from me. But here is, we'll just start filling some of this out, and then I'm going to go between this and the PhET, molecular structures, in order for you to be able to visualize those. So A is the central atom in a molecule. X is something else that's bonded to the A, and then E is the lone pair electrons. So my first example is just AX. There's one bond, there's no lone pairs. This would be linear. The electron geometry, you can take this line out, is linear here because there's only one or two domains, which mean one or two total bonds and electron pairs. An example of a linear without any lone pairs would be hydrogen, diatomic hydrogen. And yeah, we'll leave it at that. Next one, AXX. So now, again, no lone pairs, just two bonds. So this is going to be linear. Example of this could be carbon dioxide, which is double bond O. So we only count those double bonds as one domain. So there's a total of two domains here around the central atom. We could also include beryllium bonded to hydrogen. This is an exception to the octet rule. So there's no lone pair electrons on the beryllium. The beryllium is okay having 4 valence electrons. And then one more linear would be A bonded to X with a lone pair. So we can put a lone pair of electrons. I'm going to circle them for this video just to really point them out. This would still be linear. An example of this could be the cyanide ion, which will, if we can pick either carbon or nitrogen to be our central atom. And you can see that if I have, let's say carbon is my central atom, it has one bonding domain and one non-bonding domain. So it does fall under this AXE generic formula. Next, we're going to talk about trigonal or trigonal planar. These are all going to have 3 domains, and this is sp2 hybridization. And the bond angle is going to be 120, or it could be a little less when you have those lone pairs that compress the shape. So I will draw on here, and then I'm going to show you on the PhET too. So this would be A, X, X, and X. The bond angle here is 120. The shape of this is trigonal planar. And an example of this, a lot of times boron is a good example because it's an exception to the octet rule, and it will end up with just those bonds. It doesn't have to be boron. There are times where carbon does this, where it'll have 2 single bonds and a double bond too. But let me show you the FET. This is a trigonal planar molecule, and you can see the sticks are representing the electrons in the bond. A would be, the orange colored sphere in the middle. That would be our central atom, and it would be boron if this is BF3. And you can see that it's planar. It is flat in space. It does not bend. It stays, very flat. So I am going to check the geometry and the, let me move myself. Can I? I don't know if I can get my video out of there. Yeah, we'll leave it at that. So that's an example of a trigonal planar shape. Let me show you another. I don't know if I have one here, actually. We'll go to the real, or the down here. So I could give you another example. This would be trigonal planar, and it is a bent shape, also known as a V shape. The angle right here is going to be a little less than 120 because of the lone pair electrons on the top that are compressing. So let's go back to our sheet, and now I can't find it. Let me grab it. So I'm just pulling it up again. So in the trigonal planar, there's a trigonal planar molecular shape, there's a bent, and there's a linear. So let me show you. Here we go. So the first, we just did trigonal planar on the shape. Now we're going to do the bent. So we can have a X, X, and then there would be one lone pair of electrons. So this is bent. And an example of this would be ozone, which is O3. It has a single bond and a double bond, and then it has a lone pair. So on the central atom, the middle oxygen, you can see that it has 2 bonding domains and 1 non-bonding lone pair. Linear, we can also have A bonded to X, where A has 2 lone pairs. So this is going to not have a 120-degree angle like the rest, because in order for it to decrease the repulsion, it's going to go into a 180-degree angle. An example of this would just be diatomic oxygen. Now we're going to switch to tetrahedral geometry, which is 4 domains total. And the first one is going to be just a regular old tetrahedron. On paper, it does not look tetrahedral. The angle between is 109.5 degrees. And it does have the tetrahedral shape. An example of this would be methane or carbon tetrafluoride. A lot of times it is carbon in the middle. It doesn't need to be, though. I'm going to keep going on this, and then I'm going to show you on the FET. So another tetrahedral, total of 4 domains, could be 3 bonds and 1 lone pair. This is called trigonal pyramidal. An example of this is ammonia. And then it's also possible, again, we have 4 total domains. to have 2 bonds and 2 lone pairs. And this is going to be a bent, or the book calls it a V shape. Water is a classic example of this. And then lastly, we have another linear, so this angle is not 109, where we would have 1 bond and 3 lone pairs. And this would be linear. Example of this could be HF. F would be our central atom there, and then bonded to the hydrogen. So let me show you on the PhET, and then I will quit the video, and then I'll make another video where I show you the domains of 5 and 6. So let's go, let me show you. So tetrahedral example here, here's methane. So you can see on paper, it does not do the justice here. You can show the bond angle and you can see that it's 109.5. If I look at a trigonal pyramidal, this is that lone pair on the top. Remember, that requires more space. So you can see our bond angle is a little bit less than 109. And then I don't know if I have a bend. Yeah, water. So here is water. Again, it has 4 domains. It is in the tetrahedral geometry, but this is the bent shape. And again, those lone pairs are compressing, so you can see that bond angle is smaller than 109.